First of all, we say that as I am from Strasbourg, I'm very happy that you are here, and I wish to welcome you warmly. This afternoon, we'll speak about nucleosynthesis of the element still oxygen-16. Où est-ce qu'on... Attends. C'est ici. Voilà. This chart I am presenting you know already. We can say that hydrogen and helium are most common, and other elements like lithium, beryllium, boron are not. Then also two other things we should note is an alternation of abundance of elements according to whether they have even or odd atomic numbers. This could indicate maybe that there are alpha particles in the nuclei. And also a general decrease of abundance, this is clear. But before speaking about nucleosynthesis, it's useful to see how the neutron and then the proton and the electron are yielded. According to my theory, it's my theory, so it has to be discussed, of course. I exposed to you in Stettin last year the Higgs boson mass yields the neutron mass and in the following way. Here I have modeled the Higgs boson mass. This mass is the intrinsic mass of the Higgs boson of 126 GeV. You see on the chart how I did it. Actually, I noticed that there is a core of 1,800 electrons in the nucleon, and multiplied it by the famous alpha fine structure constant, which is everywhere in quantum physics, and nobody exactly can explain it, but maybe we can explain this when we see the difference of mass of the nucleon and the Higgs boson. And also maybe we could even look for the mass which is lacking and even the energy lacking, but this is another story. So this Higgs boson, I modeled it like that. Let's say, you see, there is a core of two 1,800 elements, and also other elements, which are these of the triangle. So this model of the Higgs boson is based on that structure. And I will show how this structure could yield the neutron and the proton structure. This is a summary of that process. I call massification demassification, but this is nothing else than what we call, let's say, the loop quantum gravity. Actually, if there is at each Planck instant a massification occurring and then an immediate demassification, it has, of course, an implication on gravitation. We do not notice because it's at the Planck instant, of course. So upstairs here, you can see I have modeled the summary of the Higgs boson, the things I just show you on the table. And beneath, there is another table which models the neutron. The neutron is structured according to my theory, again, like that. We'll see how it works. So how is this neutron mass determined? There is first a process of, I call massification, demassification, actually loop quantum gravity. If we look, if we look at line 18, which is here, look at line 18, we can see the evolution like that. This line 18 was first the line 1, and then 2 and 3, etc. And the evolution is the following. Evolution of line 18. First, the massification is giving a result of 100 plus 1. There is a demassification which occurs a Planck instant later. And it's the reason why the mass exists, because if the mass was absolutely equal to the anti-mass, I call it, we would not exist. But there is a system, a sort of mechanism, which permits to the mass to be prior to the anti-mass, not as such, but in the time. The point is that the mass and anti-mass are absolutely equal, but not in time. It's the reason why mass and time are linked, the baryoning mass. So this evolution is going till line 18. Here, line 18. And we find that number, which is just 1.01 power 17. Table 3 gives you the same in detail. You can see that this is divided according to powers, 10 power 0, minus 2, etc., till minus 34. Why? Because after that, we have, let's say, the normal mass, no longer quantum mass, because we come at the 10 power 38, which is the difference between quantum and normal mass. So this is the detail of all that and how it works. Of course, very schematized. There's another table, but it's practically the same. These two tables represent the neutron, which is constituted with this trunk of 1,800 electron masses, and 3 half of the mass of table 3 and 1 half of table 4. This is a detail, but it's important for the calculation only. The structure, which is shown on this table I just showed you, enables me to determine the mass of the neutron, then that one of the proton. What is important, the dipolar magnetic moment correlated with the mass. Actually, if you look at the system of massification, demassification, or the system of quantum loop gravity, you can also have a subproduct, which is the dipolar magnetic moment from the neutron and the proton. And, of course, last but not least, the binding energy of the various chemical elements, as we will see, because this is important for LE and R. What is also important, I come back to others, is to see that there are some poles and lines I will detail. The neutron is then constituted with a trunk of 1,800 electron masses and 2 poles of, in fact, 4 poles divided by 2, which are determined in the following way after this calculation. Each average pole is equal to 9.872 MeV. Also, there are 3 multiplied by 12 by 18 lines and 1 multiplied by 17 for the neutron, for the proton, it will be 18 also. And it's the reason why some elements of the proton disappeared as an antimass in energy. So we also, what you can notice that there is in fact much more mass on these lines. From 10 power 0 on line 18, there is a mass we have seen that is 1 plus 17 power minus 2, etc., etc. This mass is a result of a mass which is 100 times bigger, because it corresponds to the Higgs boson mass. And the system of massification, demassification is reducing it to 1%, as I said. This is the case for the whole neutron, actually. So when the antimass of all the lines is removed, that mass is equal to the mass of the whole neutron. We can recover the mass of the whole neutron. Sorry. We could recover the mass of the whole neutron. And this is very important, as we will see. And only for the poles, of course, not for the core. And when this happens, once for the neutron and twice for the proton, there is a helium-4 nucleus which is appearing with loss of 1 neutron pole and 2 proton poles. The loss is equal to 28.325 MeV, which is the binding energy of helium-4, as we will see. So binding energy of helium-4 and others, actually for mass theory, is only necessary to have 5 elements. First of all, we can determine with this system of lines and poles the binding energy, the binding energy of deuterium. I call NP, which is equal to 4 lines. Which is equal to 4 lines, because one line has a mass equal to that. And this is the number we know, 2MeV 2246. Then that one of helium-3, I call NPP because there's a neutron and 2 protons, which is that one, which is equal to 1 pole of neutron plus 1 pole of proton divided by 2, minus 4, let's say, the 4 lines of the deuterium are recovering mass. So the mass of, or the binding energy of helium-3 is that one after my calculation. The same for tritium, I call NNP because there are 2 neutrons and 1 proton. This is equal to 1 pole of a neutron and recovering 1 line, 2 lines, 3 lines, 4 lines, depending. So this is, at the end, 15.25 lines, and this mass is binding energy. Same for alpha particle. Alpha particle has the particularity to contain all the others. You have 17.75, this is 1 pole, 2 NN, 4 NP, this for NNP, and this for NPP. In total, 50.875 lines, and if you calculate, it is 25.3 MeV. On the contrary, the helium-4 has, as I said before, lost 1 pole of neutron and 2 poles of proton. This is a binding energy of 25.325. There's a little difference between the alpha particle and the helium-3. It's it's a little difficulty. I will more skip for the present time. And we will go to the structure of helium-4, which is, for me, the element which is important. I have figured here a neutron with a core of neutron and 2 poles. One pole, as I said, will be lost to become another neutron. So I will explain later how this is possible. And will become a proton, then again a neutron, then a proton, to become at the end a proton. The second neutron will also lose one pole and become a proton, neutron, and then at the end a neutron, etc., etc. At the end, we have, let's say, found a particle, helium-4 particle, which has lost one pole of neutron and 2 poles of proton. It's figured here. The binding energy of helium-4 is that one, figured by the proton pole and half of the neutron pole. And this is 25.325 MeV. So we can say that the alpha particle is composed with the following nuclear masses: a proton and the 2 poles of the proton, neutron and the 2 poles, etc. But the mass is at the end that one. One neutron pole and 2 proton poles which are lost. So important remark now. How can a pole be transformed into a new neutron or a new proton? One notice that there is a difference. It's always. There is a difference between this type of fusion and the classical fusion. In the classical one, the poles of neutron and proton have to disappear in neutron or gamma particles to make place for the nucleons which are imported. The process I propose is different. It modifies a pole of a neutron or proton into a new neutron or proton without having to expel any pole, hence no neutron, proton, or gamma rays are expelled. This theory is in line with the process and results observed in the case of LENR. We see that in the case of the classical deuterium fusion reaction, we have this one, we will know, everybody knows, deuterium 2 deuterium, helium-3, plus neutron, high energy neutron, etc. for tritium, very rare case, helium-4. The result of this reaction is nevertheless non-stable. The classical explanation is that the 2 protons are repelling each other because of the Coulomb barrier. Nevertheless, the reaction is resulting either in helium-3 or in tritium in equal quantity and helium-4 in gamma rays in rare cases. Tritium, which should be stable as containing only 1 proton, is decaying slowly in helium-3, which is stable and as it should not be. Instead of this classical process, a new process of nucleosynthesis of helium-4 is proposed. So we begin now with the proton. It will become a deuterium with a loss of 4 lines. This is the binding energy of deuterium. The same for tritium, which is losing 1 pole of neutron and regaining some lines. encore, d'accord. The same for, yes, sorry, for helium-3. You can see here I made two models, loss of one pole of neutron, gain 4 lines, loss of 18 lines of neutron-proton. And this is this binding energy. For helium-4, we already have seen it. So this is the important point now. What about the stability of helium-4? For me, things are clear. The protons are bearing the, let's say, the essential thing of not of the mass, but of the electromagnetism. If they have lost one pole each, they are behaving like one proton, but of course with 2 different quantum states, because they are not one proton. And this is the difference, according to me, of the difference of quantum state. So now the explanation will be a little bit difficult, because I have to call again to my, I have to call again to my explanation on the Higgs boson. The point is the following. In case of in case of 2 protons, the first proton expels. Sorry, it's a preferred pointer because it's not so sensitive.
Need 2 pointers.
Yeah. Yeah. Sorry. Yeah. Actually, the point is the following: the electron is not alone on an orbit. Actually, each time an electron is produced, and an antimass is immediately eliminating that electron in an antineutrino. The antineutrino has a mass and an antimass, but it's a former electron, basically. This is replaced by a second electron at the Planck state, Planck time instant, and this is again eliminated or absorbed by the antimass, etc., etc. So there are not one electron but a lot of electrons which are always absorbed by the antimass. As a conclusion, we can then model all the nuclei with the binding energy I have just given. Let's say the deuterium-1, the tritium-1, helium-3-1, and helium-4-1, of course, alpha particle. This I have done, for instance, for oxygen. You see, oxygen has 4 alpha particles, and are bound, these alpha particles are bound by 2 NN. Let's say this is 1 pole of 1 neutron, and 2 NP, this is deuterium-1. And if you make an average, it gives this picture. And this is the basis of my calculation, and the rest you can find on my posters, which are outside.
Yeah, 1 minute left.
Yeah, okay, I finished. I'm finished, thank you.
I'm sorry.
No.
So the floor is open for discussions. Any questions before the lunch? Yeah. Go ahead. Where is the other one? Oh, there. It's coming. No, he has one there.
Hi, Philippe. I tread here very cautiously because I'm not a theoretician of any kind. But I just wonder how fundamental to the existence of this theory is the actual existence of the Higgs boson, because I have read quite often, Unzicker, for example, in his book, The Higgs Fake, says nobody's actually ever detected a Higgs boson per se. They've inferred the existence of a Higgs boson from the perturbation of something else. I just wondered if you wanted to...
Of course, there is a Higgs field. I fully agree with you. It's very simplified what I said here. But actually, there is a Higgs field, but we have detected a sort of Higgs boson which has a mass and which gives a mass to the other, to the rest of the baryonic mass. So for me, the question was how to relate the mass of the Higgs boson to the baryonic mass. But it's true, there is a Higgs field.
Controversial.
Sorry?
Controversial.
Controversial. Everything is controversial in theory.
D'accord.
As our friend Jean-Paul said, yes, there are theories and theories. Maybe we can discuss. Maybe it's wrong. Maybe this is partly true. What I can say that I have, thanks to that, I have derived the mass of the neutron, the proton, the dipolar magnetic moment as with the same system. I can show you. This is
yes,
I can show you. And second, I can model all the binding energies of the elements with very easily. This
so
I can say.
You have begun from the top and worked your way down to the bottom.
Yes.
Yeah. Other theorists, of course, have begun at the bottom and worked their way up towards
This is
the
the
top.
Anglo-Saxon way.
Yeah.
You see, but I am a special guy. I am French, but I'm also German because I'm from here. And the German and the French are terrorists, and I am double terrorist, French and German. Sorry.
Whereas, thank you. Perhaps the English are not theorists, but merely terrorists in the scientific field.
The English have always won because they're pragmatic.
Can you pass it to Jean-Luc here?
I have just a question. I am very disturbed by the question of antimass.
Tu peux parler français, après je parle anglais.
Ask the question in French.
Je suis très perturbé par ta notion de antimasse. Je pense qu'il est peut-être possible de s'en passer, à mon avis.
Yeah. Actually, what is the Higgs boson process of giving mass is, of course, challenged by another process. In physics, we know that there is an action and a reaction. The action, for me, is what I call the massification, the creation of mass. There is an immediate reaction, which is the destruction, annihilation of that mass. But immediate does mean, in quantum terms, 1 Planck instant later. You see, the first lesson of physics I got when, with my teacher when I was at school was that action and reaction is the same. That's true, but not the same in the time. This is my point. An action comes first, and the reaction comes later. If there is to any action there is a reaction, we can say that at the end, in the time, there is a little advantage, a break of symmetry, if you may say so, a break of symmetry of the mass compared to the antimass. And this is only true in time. This means that if you can go outside time, this does not exist, but there is no mass outside time, I would say.
As in the work of M.E. Noether, of course,
Okay.
who introduced the concept of time into thermodynamics. Similar.
Yeah.
Okay, yes.
Okay.
I think you can talk later together during lunch.
Oui, écoute, on va parler en
It's time
français
to go
après.
for lunch. It will be
Non,
easier.
je te conseillerais de voir les travaux de professeur Max Strassler qui travaille au Grand Collisionneur.
Okay, let's stop here because you're speaking in French and nobody understands besides me.
Il a une autre théorie pour définir ça.
No, you can talk later.
C'est un spécialiste
Okay,
du
thank you very
boson,
much,
alors,
Philippe.
Okay.
And now it's time for lunch. These guys are hungry.